All right, so I've been asked about the math that we've been working on and doing a little review video. So I'll start with this picture here of a wave and the important vocabulary. So the first one would be, a wave starts, we call it the origin. I just Googled this. They call it the median line. So we call it the origin. It goes up from the origin, back down, and then up again. So you could call a wavelength essentially the distance of one wave travel. So it starts here and ends there, crest, trough. And then the wavelength can be defined as the length of one wave. Now, normally, though, just because it's, I guess, up high, we define it as crest to crest. You could also say trough to trough. But it isn't measured in the standard distance metric unit of meters. It is given the Greek symbol lambda, lowercase lambda. Okay, so that's the distance the wave travels. Now, if you were standing at this point right here, you could count how many waves would pass per second. So you're counting, now you really wouldn't be because it would be too fast. But that is called the frequency. So the frequency is the number of waves that pass a particular point per second. Waves per second, cycles per second, or given just the unit of 1/seconds. Renamed after a scientist, Hertz, Hz, so always capitalized because it's after a scientist. And that is given the Greek symbol, looks like a funny looking V, the Greek letter nu. So we have lambda and we have nu, and the way they are related is by the speed in which this thing travels. It travels at the speed of light, c. So we say lambda times nu is equal to c. So there's our first equation. Very simple equation, 3 variables. So 3 variables, you're going to have one of these two, so either lambda or nu, and you always have c. c is equal to 3.0 times 10 to the 8th meters per second, so the speed of light. So now if we know lambda, we can solve nu. We know nu, we can solve for lambda. So let me show you a calculation involving that. So a photon has a frequency of 6.0 times 10 to the 14th hertz. Convert this frequency into wavelength. Now we're going to add a new unit of measurement, which is nanometers, because we're going to compare it to the visible region. Can we see it with our eyes? If it's within a very narrow range of nanometers, we'll be able to see this as we've been doing, looking through things with our spectroscope over the past few days. So, all right, so the equation, very simple. There it is. C is 3.0 times 10 to the 8th meters per second. We're given a frequency. The frequency, there's that unit of hertz, which is 1/seconds. So that's nu. So we're looking for lambda. So lambda times 6.0 times 10 to the 14th. I'm going to rewrite hertz as 1/seconds so that when I divide both sides by 6.0, the 1/seconds and the 1/seconds will cancel, and my wavelength is going to be in meters. Let me grab my calculator here. So 3 times 10 to the 8th divided by 6.0 times 10 to the 14th, and I get 5 times 10 to the minus 7 meters. Now, as I said, we want to compare it to the visible spectrum. So the visible spectrum, I'll show you it in a second, is in nanometers. And we're going to get a conversion, which is 1 meter, 1 times 10 to the 9th nanometers, and I'll show you that in a second as well. So multiply then my answer here times 1 times 10 to the 9th, and I get 500 nanometers. So now the question is, can I see it? Is it within the visible region so that my eyes can detect it? And then I'm going to add some other things here. But you can see this right here. So this chart is the visible spectrum in nanometers. We just got an answer of 500. So the question was, can we see it? Is it within the visible region? We can see that it is. It would fall within 500 nanometers, falls within the green range of Roy G. Biv. So Roy G. Biv going in that direction. So yeah, the answer to that is yes, we could see it. All right, so now the second thing that we learned concerning frequency and wavelength is the energy of the waves. So energy is equal to a new formula. E, energy, is equal to H, another constant called Planck's constant, 6.626 times 10 to the minus 34 joule seconds. So that's always h, just like c is a constant, h is a constant. There's our frequency again, is equal to energy. So energy is going to be measured in joules because of the unit. The 1 over seconds of the frequency and seconds will cancel, and we'll get joules. So now we can relate frequency to energy and then to wavelength. So as long as we know wavelength, frequency, or energy, because of Planck's constant and the speed of light constant, we can actually calculate the other two. If we know one of them, we can calculate the other two. So then we related it to this idea of Bohr's model of the atom. So where the model of the atom shows, and we've been developing this now for a few weeks, Coulomb's law, photoelectron spectrum, PES. So each of these crazy circles here represents one of the energy levels. Schrodinger's equation, talking about quantum numbers, n equals 1, 2, 3, 4, so energy levels. And then you can see these transitions. So this electron, which is in the 4th energy level, dropping down to the 1st level. So we hit an atom with energy, specifically in this case the hydrogen atom. The electrons would absorb energy. We say it goes from the ground state to an excited state, immediately drops back down and gives off a wave of energy. If that wave of energy falls within a very narrow band, the visible spectrum, we will be able to see it. Now, if it doesn't, it might be in the UV. So we have violet down to red, so Roy G. Biv inverse. Outside of the violet, a little bit shorter wavelengths than 400, we have ultraviolet. Outside of the red, we have infrared. And we need another equation then that shows us this energy of this photon, or this energy that is released when the electron drops from energy levels. And that equation I have down here at the bottom, but I'm going to switch slides here and we'll look at it on our formula sheets. This is what we're going to have in our quiz tomorrow. So there's the equation. So E, or delta E, change in energy, meaning going from one level to the other, or just the energy that's given off, E, is equal to negative 2.18 times 10 to the minus 18 joules. And that's called the Rydberg constant. So another constant that doesn't change. A little lag there. Times 1 over n final squared minus 1 over n initial squared. Where final is, where does the electron end up finally, and where did it start initially in terms of energy level, n. And notice it's squared. All right, so look at my example here. Calculate the wavelength of a photon emitted by a hydrogen atom when its electron drops from 5 to 3. So it's going from 5, so that's the initial, to n equals 3, the final. All we do is plug it in. It's a very simple calculation. Negative 2.18 times 10 to the minus 18 joules, the Rydberg constant, times 1 over the final. So it went from 5 initially to 3 finally, so 1 over 3 squared minus 1 over 5 squared. So the energy is equal to, we just solve. We have fractions there, but we could just make them decimals. Let me get my calculator back. So 1 divided by 9, 1 divided by 25, 0.111111 minus 0.04 times 2.18 times 10 to the negative 18. And we get, now notice it's a negative sign here, so really we get negative 1.55 times 10 to the minus 19 joules. But as we talked about, it's not really negative energy. It means thermodynamically that the electron is losing energy. If it was positive, it would be gaining energy. All right, so now I know the energy of the photon. So I used Bohr's equation, figured out the energy that is given off when it drops from 5 to 3. So now I can use this to solve two more equations. E equals h nu. I know the energy. Solve for the frequency. And then lambda nu is equal to the speed of light. I know the frequency. Once I solve that, I can now solve for the wavelength. And then I can see whether it's in the visible spectrum or not. All right, so I don't want to carry the negative sign over because it doesn't make sense to have the negative wavelength and frequency. So again, that just tells us which direction it's going. And this negative in front of the Rydberg constant takes care of that for us. So E equals, let me give myself some space here. Get rid of this. So E equals 6.626 times 10 to the minus 34 joule seconds, the Planck's constant. And I want to know what's the frequency. So let's solve that. Again, back to our calculator. Again, nice, easy three-variable equation. I know the energy, I know the Planck's constant itself, so we're going to divide that way. So that answer that I have there divided by 6.626 times 10 to the minus 34, and I get a frequency of 2.34 times 10 to the 14th, 1 over seconds, or hertz. So now I know the frequency of the wave. I can now, just like that equation before, plug that into this equation, equals the speed of light. The 1 over seconds and the 1 over seconds will cancel. I'm going to get meters. Once again, simple three-variable equation. So 3 times 10 to the 8th divided by my answer from there now. And I get 1.28 times 10 to the minus 6 meters. But I want to be able to compare this to the visible light spectrum. So I don't want to leave it in meters. 1 meter, 1 times 10 to the 9th nanometers, times 1 times 10 to the 9th nanometers, and I get 1,282 nanometers. So the question is, can I see it? No, I can't see it. It's outside of that visible range. But notice right here on the Bohr equation, I do have a 1282. The reason for that is this is the transition we just did. Follow that around, n equals 5 is dropping down to n equals 3. So this was the exciting thing about the Bohr model, is now they had an equation to explain the line spectrum of hydrogen. And as we discussed in class, how that affected things. So now here's the spectrum that we saw. We turned on the spectral tubes. We saw the line spectrum of hydrogen. Remember ours, these two were combined because of our cheap little spectroscopes. But these are the 4 lines that you see within the visible range of the hydrogen atom. So now here's the great thing about this. This is in nanometers. So let's say I want to look at the red one. I would say, you know, reading this, maybe, what, 660 nanometers, would you say? I would know the frequency, or the wavelength. I could use that equation to solve for the frequency. And then I could use this equation to solve for the energy. I'm not going to do that. You want to do that equation, that calculation, you certainly can. We've done enough of them. If you have any questions, I know it's fast. People always say that. That's what Rewind's for. Because I want to get through it, you know, not stand here for 40 minutes. So there it is. Let me know if you have any questions.